All right, we're going to go ahead and get started, I think. So in case those of you who don't know me or haven't met me, my name's Chandler Carruth. I work at Google. I lead the Clang and LLVM group at Google. And I'm here today to talk to you a little bit about LLVM instead of Clang and about optimizations. I want to preface this by saying I think that I might have maximized my ability to come up with a bad talk title, and I apologize for that. But what I want to talk to you about today is really the problem we have in LLVM of optimizing C++ code, which has a lot of abstractions in it. And we're going to do that mostly through a case study about hash value. All right. There we go. So what code matters? That's the first thing we really have to think about before we start talking about optimization. What code are we trying to optimize? What domain do we care about? There's a lot of different things out there that we could try and do. I mean, everything from Fortran loop-heavy code all the way to encoding and decoding and kernels, like loop kernels, and big projects or small projects. And for me, what I care about tends to be C++, servers with lots and lots of threads, and really big code bases, right? Really big C++ code bases. That is the primary focus of all of the stuff that I'm looking at. And so understand everything I'm about to say is within that context, right? Different context, different set of answers to different questions. So how does C++ scale up to these enormous code bases? Mostly, we do that through abstractions, right? That's how programmers reason about everything. It's like if you have a problem, right, add another layer of indirection, and you can solve your problem. Unfortunately, abstractions have a cost. They aren't exactly free. And when you start thinking about how code and abstractions and complexity grows over time, you're going to realize that as the number of people working on a project grows in a fairly linear trend, you remember Clang's nice linear trend, right? This is what we study to get there. Right? But the lines of code, and in fact the complexity, ends up growing in a superlinear way. And the reason is that the lines of code tends to correlate with the amount of time spent writing code. And as the number of people grows over time, all the people that have been there keep writing code that entire time. It's a compounding problem. So if we're going to address complexity in C++, we have to be able to address really superlinear growth of complexity in C++. Now, the classical idea of how to do this is through the idea of zero-cost abstractions, right? Like we should only pay for what we actually use when we're using C++. But it doesn't always work out that way. Zero-cost abstractions require a lot from the optimizer, okay? And here are just a few of the optimizations that are critically important to getting zero cost out of your abstractions. And I'm going to focus on inlining today because that's the most important of all of these, right? So if we look at all of these are all interesting, but inline is going to be probably the single most important. And we'll talk more about why that might be. So our case study is about hash value. I don't know if you guys were paying attention to the commits, but sometime in the past year, I can't remember when, February, I think, I actually started working on LLVM's hashing implementation. And in order to even talk about this, I need to first explain what on earth the LLVM hashing library is doing, because it's a little bit surprising to people. So the interface looks something like this. It's really complicated. There are lots of ins and outs. But the interesting thing here is right at the bottom, right? So think about this one here, which just hashes pointers. The goal of this is to pull out this hash code object, which we can use in building a hash table like dense map or any other hash table, right? We want to have a hash code object for some data that we're putting into it. And in LLVM in particular, the thing we care most about are pointers. We use pointers as the keys for our hash tables more than anything else. So the really interesting thing for this talk are these two functions, hash combine and hash combine range. Because while the user interface, right, is this hash value stuff that's very templated, the actual implementation of hash value functions, the way we build these hashes are through these two helpers. And it turns out they're a lot harder to implement than I ever anticipated. OK, so we're going to start with a simple implementation, all right? A very simple implementation. This is Dan Bernstein's hash. It's really, really boring. Lots of people know about it. And in fact, we use it in certain places inside of Clang. So this is really boring code. It's a loop. The optimizer knows exactly what this is doing. And by the way, through all of these examples, I've simplified the routines a little bit. Forgive the terrible code style, but I tried to make it fit on a slide. Now, this very simple routine, unfortunately, performs really badly for strings of more than 1 or 2 characters. And I mean really badly, because it's a character-by-character operation. And we can do a lot better algorithmically. If we know something about hashing, we can come up with something that's much better. Unfortunately, when we go to write the code to do that, the code isn't going to fit on a slide. It's pages and pages and pages of code. And so we need some abstractions in order to even reason about this once we start adding that kind of complexity to our hashing. All right, so now I'm going to walk through some of the abstractions that I added, and just some of the abstractions that I added in order to implement this. And then we'll see what went wrong with optimizing them. So we start off with adding a lot of complexity to hash combine range, like tons of complexity. It doesn't even matter what all this is, because remember, we hash pointers more than anything else. Right? So the interesting thing here is when we check if the length is 64 and we go to hash short, most of this code ends up being dead. Right? Hash short is even more goofy abstractions here. So we have to actually split it out into each little bucket of size. And you'll note that the very first check, right, is the length between 4 and 8. Right? Guess what pointers always satisfy? They're always 4 8-bytes long in LLVM. And so then we eventually get down to the actual implementation of it, which looks something like this. Following me so far? OK. So these are the different pieces of code we have. And the question is, what happens when we want to optimize it, right? Because ideally, what we end up with is this math here in the middle function, which is a really tiny amount of math. Right? And that should be like 10 or 20 instructions, really, really small. It gets inlined. All of this boilerplate, all of these abstractions that we're using vanish, and we don't pay for them. Unfortunately, that's not happens. Even when we only hash 8 bytes, we hit disasters. So let's look at the first disaster that we hit with trying to just fold away these abstractions. We inline everything. So the very first thing we do is we say, like, OK, these are all trivial functions. So all of this code gets flattened into the bottom function. That's actually pretty good. That was a good call. All of this code should be flattened into this bottom function. So then we get to hash short, and we do something terrible. We inline every single one of these functions, right? Hash 4 to 8 bytes, 9 to 16, 17 to 32. Every single one of those gets inlined. And the 33 to 64 byte hash function is huge. It's way more than we ever wanted to inline. And now this function is enormous, and it's really slow. And the optimizer goes and does a bunch of other stuff that doesn't make a lot of sense. It hoists a bunch of common expressions up above all of these checks. It's not what we wanted to happen. And once we've done that, when we hit the bottom of this tree, right, that place where we wanted to just call hash sort, we can't, right? We can't inline there. We can't fold that. We know we have only 8 bytes of data, and the optimizer just gives up and it goes home. OK, so how do we fix this? Well, it turns out that LLVM is not just a bottom-up inliner. Most people think of LLVM as having a bottom-up inliner, and that's the primary way it works. But it's also a top-down inliner, which is a little bit confusing. And the reason that there's top-down inlining is because you don't always want to do bottom-up inlining, because you can cause this type of code explosion. What you really want to do is you want to look both at doing a bottom-up inlining and a top-down inlining, see what the choices are, and actually balance the trade-off. And LLVM's inliner is really good at this, except for a really annoying bug that caused it to not ever try to do the top-down inlining on this particular code. So we fixed that. Yay, OK, now the inliner is actually doing this balancing act between bottom-up inlining, top-down inlining. We've gotten a little bit closer to do this. Disaster number 2, though. Turns out that wasn't even close to enough. That was the least of the problems that this particular code suffered from, because when you're inlining, the context is everything. Let's back up a second. Let's think about what inlining is doing. The whole purpose of inlining is to take a routine of functionality, to inline it into something that's using that functionality in the hope that the way that functionality is being used allows us to simplify all of the logic, allows us to combine things, reduce things, delete code, and everything gets smaller and faster. Well, LLVM's inliner was written context-free. Okay? So when it would look at a routine like this, what it would say is like, OK, we have a few parameters here. We're going to summarize the context that we might have as which parameters might be constants. That's the only contextual information it looked at. And then it looked at this function and it said, well, depending on whether length is a constant, we might be able to delete all but one of these basic blocks. right? Because if length is a constant, we'll be able to pick exactly which branch we end up in. But it doesn't know which constant. And so it doesn't know which basic block. And so the way it actually evaluates this is to average the sizes of each of the basic blocks and assume, well, it'll be approximately that, maybe. And then you come and you try and inline it, and it doesn't work at all. Because if you look at one of these, some of these are going to be enormous. This one is 10 times larger than the one we actually wanted to get inlined. So the average is completely wrong. OK, so this led to the inline cost rewrite. And the idea of this rewrite was to try and make the cost analysis be context sensitive, because that's what allows us to actually look through these layers of abstractions and actually tease apart what it is we can simplify, what it is we can actually optimize aggressively. So we first removed all of the per function cost analysis, and instead we do the cost analysis on a call site. Then, we walk through the instructions, we look at every single instruction in the function, and we try to understand how that instruction will actually behave given the context of the call site, right? We take the exact constant values we have for a particular call site, and we propagate these all the way through. There's a lot of tricky code in there. I'm not going to go into too much details. But the idea here is that we can get essentially perfect dead code elimination, because we can actually look at every single constant, every branch on a constant, and we can figure out exactly what code is going to be live for that particular call site after inlining. Because we know what code is alive, we also know the cost much more accurately. And when we look at this function, we're going to take length. We're going to take the exact constant. Right now we're talking about like an 8-byte pointer, right? So this is going to be 8. We know we're going to hit this branch, and we know we're only going to see the code from inside of this top routine. Pretty nice. Make sense? OK. Disaster number 3. I have to come in again. We still can't actually optimize this, because it turns out that this one's pretty easy. We have a constant in that length parameter that's always going to be 8. But this isn't the function that the user called. They called this terrifying function. And in this terrifying function, it followed a C++ idiom of having iterator-based start and stop parameters. Neither of these are constants. The constant is the distance between them. OK? Because of that, all of the context that the inliner was looking at was completely missed. The inliner didn't have a clue that this would simplify at all. And so it comes down and it sees this length, and it says that length's just a variable. It keeps all of the code. It recurses all the way down. There's a loop here. It's actually even worse than that, because it inlined a bunch of the loop in the bottom of this function. The other thing you'll note about this that's really unfortunate for the optimizer is that this function's written inverted from how the optimizer wants it. The hot path is out of line. The cold path is in line. And I looked around a lot of code, and it turns out this is really common for programmers. They don't like doing hot path be in line and cold path be out of line in a lot of cases, because the hot path is often simpler. It's easier to comment and document in a separate function. And they want the generic algorithm to be what's in place, because that's the generic logic. So this goes very, very badly. So finally, though, we can achieve victory, because if you look back at this, I made another change to the inliner to actually track the pointer differences, to try and model this C++ abstraction of iterators directly in the inliner. So when the inliner comes and sees this at a call site, it's actually going to look at all of the pointer arguments. It's going to find all of the pairs of pointer arguments which have a constant size difference between them. And it's going to add that difference to the context which the inliner uses to simplify the function. Because it does that, it's going to come down. It's going to see this stood distance. The stood distance folds completely away. And we actually see the subtract between start and stop. And we see the length comparison. We know that that's constant. We know that all of the rest of the code is dead. And we only look at hash short. And this allows the inliner to do a much, much better job. OK, so we've achieved victory here. But we've only talked about one of the problems. So we've only talked about the hash combine range. Hash combine, it turns out, is even harder to optimize. So we're not even close to done actually making this work. And I hate to tell you this, but this isn't solved. I don't have a solution to this problem. Because as far as I can see, it requires doing partial SROA of a struct and doing store load forwarding across method calls to realize what constants exist. Yes? SROA is the scalar replacement of aggregates, and so it's taking a big structure of aggregate data and finding a few SSA values and lifting them out of that structure. That's partial SROA. Okay. So let me explain with the actual example. So this is what hash combine ends up looking like in C++11. And the really scary thing to me is that this is something that C++11 made a lot worse. So in hash combine, what we have is this nice, variadic function template. It's really pretty, right? Thank you, Doug. All right, and then we have, all right, and now we have this recursive helper, because the way that variadics work is that they kind of recursively peel off, the arguments, and they build up the state necessary to produce an answer. So up at the top is a vague sketch of what this recursive helper might look like. It keeps all of the state that we need as we go through this, right? And it has its own variadic, and it's doing that kind of recursive peeling down. There's a base case as well that isn't particularly interesting. And the really frustrating part of this is every single call to hash combine has a constant size. Every single call has a constant size. And the LLVM will never get this right, because it can't see that this length up here is going to end up being constant. That's computed, and it's not just computed, it's computed recursively. There could be a Turing machine there for all the optimizer knows. There's absolutely nothing LLVM can do here. And so if you actually look at the implementation that's checked into LLVM, you won't see this code. You'll see code that is a lot uglier, that has manually lifted all of the parameters which need to be analyzable in the inliner out into separate parameter variables instead of being in the struct. The struct only contains the raw hashing data so that the inliner can actually see this, and it can fold down this recursive tree. And to drive home exactly how important this folding of the recursive tree is, because we have this nice variadic pattern, this is a really easy way to cause something very fundamental like computing a hash code to involve somewhere between 10 and 50 function calls. It was one of the slowest things I'd ever looked at in terms of how much code you wrote and expected to execute versus the actual cost that the program paid. Okay. So we're actually not done even if we address those two. So we also have a fundamental problem with the inliner. And the fundamental problem with the inliner is that it's not aware of link time optimization, and it's not aware of the balance between top-down and bottom-up inlining. And so right now, when we do link time optimization, LLVM is going to do something really unfortunate. At each translation unit, it's going to aggressively inline functions, assuming that they're going to become external functions. We can't go and see their users, right? And so the best we can do is to just optimize the daylights out of that external function so that if it gets called, we'll do the right thing. And this loses a lot of information. It destroys opportunities for the optimizer later, because as it turns out, we're not done. We're going to link all of those modules together in the link time, and we're going to then rerun the inliner. This doesn't work well, okay? So a lot of LLVM's passes are really nice. They always canonicalize. It's always possible to recover anything you lose. The inliner is not one of these. And so we've got this kind of tension between LTO optimization versus the normal optimization strategy. We also have a problem because programmers do this code inversion, right? So if we go back to my terrible code example, this code inversion is really unfortunate. We would like to have the optimizer reverse this code for us. But we don't have a good mechanism of doing that, because that's not inlining, that's outlining. It's the reverse process. And so until we can actually push code out of line, the inliner is kind of bound to always make code bigger. It's just going to keep making code bigger without the expected performance benefits. And so we have to actually be able to do the reverse process. All right. And finally, we do need to do merging because, again, C++ is templates. So the final problem that I ran into with this is that all of the functions I have described, everything in hash value, right? These are all function templates, which means in every single translation unit, we end up with about 50 copies of the same code, which is really, really annoying. It's incredibly important that we have the ability to merge together equivalent functions that came out of differently typed, in the typed routines in the strong type system of C++. Once we get down to something like IR, where we lose a lot of the type information, where we have opaque pointers, and we can come up with a nice generalization of the function. And hopefully, if we can do that, we can actually go through all of these abstractions. We can actually decompose things. And the reason I wanted to give this talk is in large part because C++11 is making this worse. And for good reasons. We got a lot more abstractions like variadic templates, and so it's increasingly important that LLVM is able to actually fold these constructs, and it's something we need to pay a lot more attention to. So I'm done early. Do we have questions? I probably talked too fast. Any questions at all?
Okay, so
If you can use the microphone, please.
okay. All right. So first, I was going to say thank you for doing all of this, because the fact that you work on this kind of stuff is exactly why we beat a lot of vendor compilers on complicated code like this. Obviously, there's a lot more to do, and since you have time, I was going to say. I was going to say. So for the things that you don't know how to solve, can you pontificate about how we might get there?
That's a great question. OK, so I'll talk a little bit about function splitting, because this one's, I think, the hardest one to solve. I actually already wrote a function splitting pass. It works perfectly, except for the fact that we can't use it in the current pass manager. In order to do function splitting, you have to do something that is a really annoying fit for the existing pass manager structure. You need to take a function, do a deep function level analysis of it, and then turn it into two functions, which changes the call graph. That means that it doesn't really fit into the function pass structure of LLVM, because it's actually adding new functions to the set of functions, and function passes aren't supposed to be able to do that. It happens to work right now if you just close your eyes and hold your breath, but it's not going to keep working. The natural place to put a function splitting pass is in the call graph pass manager, which is actually doing a bottom-up walk of the call graph, and is allowed to do things like add new functions to the call graph. Unfortunately, we don't have a good way for any call graph SEC pass to depend on a function pass analysis. And so all of the call graph passes, including the inliner, have no LLVM analysis passes other than the module passes that are stateless to depend on. This means we do a lot of things that are just terribly stupid. For example, we will inline cold functions. And we'll inline functions into cold basic blocks. Even if we have perfect profiling information, we will not use it when we do our inlining. And we've done some studies with what GCC benefits from in terms of profile-guided optimizations. And the #1 benefit GCC gets is better inlining decisions. And that is the one piece of LLVM that cannot use profile information at the moment. It also means that we can't do things like, so the function splitting I wrote uses the dominator tree in order to do the splitting. And unfortunately, it also needs to, at times, reconstruct the dominator tree because inlining invalidates it. So we would have to teach every pass in the call graph pass manager to preserve DOM tree in order to be able to use the DOM tree in a call graph pass. And even then, it would be a hack, and it wouldn't work very well. So there are actually a lot of just infrastructure problems with function splitting. It's really frustrating. I think that the pass to actually do function splitting took about 2 days to write, and the changes to the infrastructure to enable it will probably take about a month to 2 months to actually implement at best. And they'll be really disruptive, and they'll break a lot of things, and Chris will yell at me, and I'll yell back at him, and eventually we'll have something that works, but it's not going to be fast. That's one of the problems. Function merging is actually really easy, I think. Nick will disagree with me if he's in the room. So I have a very terrible idea for how to do function merging. I think we should compute a digest of the function, like a cryptographically strong digest of the function, and we should use that as the mangling of the function. And we should add aliases and/or thunks as necessary to allow us to, actually emit the function in a really strange mangled name. But then the linker will do the function merging for us.
So as an academic exercise, have you actually figured out how much of an optimization, if you just did 4 and 8-byte hashing, what your theoretical improvement could be?
Okay. So the question, hold on. So I want to understand the question. So I actually measured the exact benefit that what I talked about had on LLVM's code base. And the benefit was it went from about 5 times slower to the exact same speed as when we used a trivial to compute hash function. But now the hash function was a much higher quality. Again, the real goal of all of these optimizations was not to make any particular program run faster, but to prevent these added layers of abstraction from slowing programs down. And I want to focus on that a little bit because it's an unusual perspective to hear people talk about in optimization, that like the goal is not to make the code faster per se. It's that you want to enable developers to keep adding layers and layers of abstractions, making their code more and more complex without paying the cost for it. Regarding, I can hypothesize how much these things are worth, but that's really just numbers out of the air. I don't have any data.
Hi. So I'm sorry for the slightly depressing question, but what you described doesn't seem to be a new problem. I mean, it's a classical problem that when you use a language which has more abstractions, well, it's harder to optimize. So yeah, it's a new problem for C++ because of the new features in C++11, but it's not a new problem per se. And the classical answer has been, well, don't use those abstractions. I mean, that's why C and Fortran are still alive. So what makes you think that this case is special, that we can actually solve this problem with the new features of C++11?
OK, so if I understand correctly, what you're trying to say is that classically we've answered this problem by not using abstractions.
Yes, exactly.
And why can't we just continue to answer the problem?
No, that's not what I'm saying. I mean, I hope we can, but I don't see what makes this instance of the problem special. What makes it more easily solvable than the classical problems?
More easily solvable?
Yes.
No, sorry, I was trying to say that it's harder to solve. My point is that C++11 causes the rate of abstractions that are visible to the compiler to grow at a faster rate than before.
In C++, but not in other languages. I mean, you have the same problems in, you know.
So, very first slide.
Yeah.
Eventually I'll find it.
Yeah.
So, what code matters? And I highlight C++.
Yeah, but you don't even have this. I mean, you have C++ and Fortran, which are languages that normally don't have this problem.
Say again?
You have on the slide C++ and Fortran, which are languages that usually don't have this problem. So it's, you know, for this domain, it's a new problem. But in other domains, it has been a problem for years, and it has not been solved as such. So that's what I'm asking. What's new?
For me, it's just that we're looking at C++ code. Our C++ code base is growing like this. Yeah. And so it's becoming increasingly urgent that we solve it, right? Because every line of code, so the line of code are growing superlinearly, right? Yeah. But the number of abstractions, because of tools like C++11, because of tools like expression templates, are growing even faster. And so we appear to be running toward a wall very quickly. And I'm trying to move that wall.
Good luck.
Other questions? All right, thank you.